So the most important spectroscopic method that we employ in organic chemistry is nuclear magnetic resonance, better known as NMR. And NMR is going to allow us to do very easily what other spectroscopic determination methods did not allow us to do. And of course that is, we are going to be able to connect the pieces now. Or if you buy into my puzzle analogy, it's us going to connect all the puzzle pieces. So remember that we identify the puzzle pieces with IR, because IR will tell us what functional groups we have. For example, if we get an FTIR spectrum and we see a broad stretch from 3400 to 3600, we know that there is an OH group in our molecule. As another example, if we see a couple of stretches between 3300 and 3400, we know that we have a primary amine, and one of those stretches is symmetrical and one is asymmetrical. Of course, we've also discussed mass spec, and remember, this is mass spectrometry, not mass spectroscopy, which means this does not have a quantum basis. So in mass spec, remember, mass spectroscopists don't like to be called spectroscopists, but spectrometrists. So mass spectrometry can tell us the molecular formula. It can tell us the molecular weight. It can tell us about stable, positively charged carbon fragments. Of course, we call those carbocations. And of course, this gives us a lot of really good information. So both mass spec and IR spec pieced together can often give me a really good idea about what kind of compound I have. But NMR is going to be where everything is allowed to come together. And so really what I want to focus on for this particular screencast is to emphasize what we look for in an NMR, and also what is the general theory upon which NMR is based. So let's first begin by talking about a little bit about NMR theory. Like FTIR, NMR is going to be based upon the quantum theory, and that is that rather than looking at vibrational frequency energy excitations, we are going to look between excitations of spin states of a nucleus. So there are some nuclei that will have an odd number of what we call nucleons. Nucleons will be the sum total of the neutrons and the protons. And just as we have an electronic spin from the Pauli exclusion principle, we can have a net nuclear spin, and this net nuclear spin is only possible when we have an odd number of nucleons. So some of the more common nucleons that we encounter in organic chemistry will be hydrogen 1, carbon 13, nitrogen 15, oxygen 17, fluorine 19, phosphorus 33, sulfur 35. In this course, we're going to limit our discussion to the two most important. That, of course, is proton Nmr and carbon 13 Nmr. So one of the primitive bases of NMR is that you will use a very large superconducting magnet, which we can do when the magnet is bathed at very, very low temperatures. And in the presence of this large magnetic field, we can induce a magnetic dipole in atoms that have a net nuclear spin. So let's consider the most abundant atom that is NMR active, that is the proton. And so you can consider the hydrogen atom to act as a tiny bar magnet. And this bar magnet will begin to align itself with the external magnetic field or against this external magnetic field. And so in the absence of this large magnetic field, these hydrogen atoms, these magnets, will just have a random type of alignment. So they essentially will be very random, and they will not be aligned with or against the magnetic field because there is no standard field. However, once I apply a magnetic field from a strong superconducting magnet, then these hydrogen atoms will be in one of two populated states. One is higher in energy than the other, and so we call the energy state that is lower in energy the alpha spin state. And this spin state, if you notice on the graphic, always results when the tiny bar magnet of a nucleus like hydrogen is aligned with the external magnetic field, which is rendered in blue. And of course, some of the atoms will align themselves against the magnetic field, and they oppose the magnetic field, and they are termed beta. And of course, there is an energy gap that when the precise amount of energy to go from an alpha to a beta spin state is realized, you will flip the alpha to the beta, so you'll promote this spin state, this nucleon. I know the arrow at all other times represents an electron, but now it's representing a nuclear particle. And then, of course, it will stay in that higher energy state for just a bit, and then finally it will relax back down to the alpha state. And it relaxes back down to the alpha state, there's going to be energy that will be emitted. When this occurs, when I promote from the alpha to the beta, then relax to the alpha and emit energy, this is called resonance. And so the term resonance has an entirely different meaning in NMR than it has in drawing resonance structures and structure and bonding and molecular orbital theory and valence bond theory. So when you have a nucleus that has magnetic property that can exhibit this transfer from alpha to beta back to alpha, you have nuclear magnetic resonance, or NMR. And this energy gap is going to be different depending upon the environment of that particular atom in the context of a molecule. For example, certain atoms like hydrogen may be closer to a lone pair or a source of electron density, and we call those atoms shielded. Others are closer to more electronegative atoms, and those are de-shielded. When atoms are stripped of electron density, they are more sensitive to the effects of a magnetic field. More energy needs to be absorbed to have them resonate, and they'll have larger energetic values that we call a delta value. We'll talk more about that in a future podcast. On the other hand, when they have received electron density, not as much energy is needed for them to have an effect exerted by that magnetic field, and their energy values that are needed for them to resonate are going to be lower. These hydrogen atoms and other NMR active atoms will be very sensitive to their environment, and that's what allows us to correlate the mathematical values of these peaks with a given molecular structure. And of course, when we have class, I'll go into a little bit more depth about the theoretical basis of this resonance flip. But for now, let's talk about what I view to be the most important piece of information you get from an NMR. So there are 4 questions that we need to ask when we're looking at the information that NMR will tell us. In my opinion, these questions are not created equal. So to me, this is the most important one. And that is simply, how many unique magnetic environments does a molecule have? Now, the most important of all of our NMR techniques will be Proton Nmr. So we're looking at unique hydrogen environments. Let's just briefly consider a simple spectrum for ethanol. Of course, ethanol has the following structure. So it's CH3, CH2, OH. And so we'll see one signal from this H, which we'll call HA. We will have 2 hydrogens that are equivalent to one another. And we'll talk about equivalency in just a couple of minutes. And this equivalency will result in a second hydrogen environment. We're going to call that HB. So here is HB. And downfield just a bit is HC. HC, it takes more energy to resonate because it's been more stripped of electron density. Finally, we can look at the methyl group, HA. And so here is a hypothetical spectrum. There are 1, 2, 3 different types of hydrogen environments in this molecule. The first skill we really need to work to master is looking at a chemical structure and predicting how many hydrogen environments exist. The best way of learning this skill, obviously, is lots of practice. And so I am going to utilize a program that comes in a chemistry drawing software that I use. This is called ChemDoodle. ChemDoodle is available for student purchase. I believe the cost is $60 for 1 year. I have drawn a simple molecule, 2-chloro-3-methylbutane. 2-chloro-3-methylbutane. Let's predict how many peaks that we would see on the Proton Nmr. And so we have 3 hydrogens here, which would be one environment. These are exactly equivalent to the 3 hydrogens that would be here. And among other reasons, they're both about the same distance from a chlorine. You can rotate around this bond, and when you rotate around this bond, these 2 methyl groups can change position, so they are equivalent one to another. We'll later learn other ways of doing this, but this works well for now. I have 1 hydrogen coming off of this carbon. That would be a second environment. I have a hydrogen coming off of this carbon that is also bonded to the chlorine. That would be a third environment. And finally, this methyl group would be a distinct environment from the previous 2 methyl groups because it's closer to chlorine. So I would predict 4 hydrogen environments. And I don't want you to look at anything other than the number of hydrogen environments when I pull up the theoretical NMR spectrum for this compound. So we said 4. I just want to expand this. Notice that the NMR is scaled, and just like IR, it does something really unusual. And that is the smaller numbers are to the right and the larger numbers are to the left. Typically we see just the opposite in a Cartesian coordinate system. There is a peak at 0. This is called an internal standard. And this internal standard is tetramethylsilane. And this has a chemical shift that is known to be 0. And so tetramethylsilane corresponds to the peak right here at 0. So we don't count this. What we do count are 1, 2, 3, 4 proton environments. Now there are a couple of additional aspects to this spectrum that we need to discuss. Remember, there are 4 questions. The first of which is, how many hydrogen environments does this compound give us? And the answer to that is 4. Notice the peaks look different. Some are taller than one another. Now, in the real world, this will not be a peak, but rather a curve. And if we take the area under that curve, it helps us determine how many hydrogens are in each environment. For example, these 2 have a total of 6 hydrogens. These will be associated with the largest peak. This environment is with 3 hydrogens. That's the next largest peak. Both this guy right here and this guy right here are associated with 1 hydrogen. Again, it's not the peak height, but rather the area under the curve that matters the most. Number 3, they are split differently, which means that they are all bonded to a slightly different hydrogen environment in the context of what hydrogens are bonded to the carbon to which the carbon they are bonded to are attached. Let me give you a quick example, and we'll use this molecule in our example. So I'm going to just put up a new slide. And on our new slide, just want to start labeling these hydrogens. And I guess it doesn't matter so much what we call them. But just so that you know where everything comes from, I'm going to draw all these hydrogens explicitly. And with D, I know there are 6 of them. 3 on this one, 3 on this one. And I'm going to talk about splitting in more detail on another slide, but just real quickly, all the HAs are the same. There is only one other hydrogen that is within 3 bonds of these HAs. 1, 2, 3. And this is HB. HB will actually interfere with the signal of this environment by HA. This hydrogen is a magnet. It can align with the field, or it can align against the field with equal probability. So this peak at HA is actually split into 2, and because each of these possibilities are equally possible, I have what is called a doublet. So HA is split as 2 peaks. If I look at HB, I've got all kinds of possibilities. First of all, I can be split by these 3 hydrogens, and if I have 3 hydrogens, I could have 3 that go with the magnetic field. I could have 3 that go against the magnetic field. I could have 2 with and 1 against. And I can actually arrange these in 3 different ways. And the same when I go 2 against and 1 with. Notice the ratio here is a 1 to 3 to 3 to 1. So by HA, HB is split into 4 peaks in a 1 to 3 to 3 to 1 ratio. But it's also split by HC into doublets in the 1 to 1 ratio. So normally when we have a quartet, it's split like this. But when I have another environment, HC, that can split, each of these peaks is split into a doublet. And so this gives us what is called a doublet of quartets, a total of 8 peaks. Now we'll talk more about this complex splitting later, and it does depend on a couple of other factors. I simply want you to see how we get the peaks that we do. So we would abbreviate HA as a doublet. We would call HB a multiplet because it's more than 5 peaks. HC the same thing because you would see 7 peaks from here and 2 peaks from here. We'll call that a multiplet as well. And HD, of course, would be a doublet again. So let's go back and let's look at our Proton Nmr in terms of the splitting. And in fact, you do see a doublet, a multiplet, and a multiplet. So we can justify this environment by both the number of proton environments we have and the way that it is split. 2 other questions we'll eventually ask in our discovery of NMR is how many hydrogens are associated with each peak. That's called integrations. And finally, why do they have different mathematical values on this x-axis? We call that the chemical shift. In closing, let me give you guys a few examples to think about in terms of predicting the number of environments, and that's really all you need to practice at this point. So I'm just going to draw a few for you. So let's do heptane. Let's do 2,3,4 trimethylpentane. Let's do this alkyne, which has 1, 2, 3, 4, 5, 6, 7, 3 heptime. And let's do one more. All I want are the number of hydrogen environments. So, in preparing for class tomorrow, predict how many hydrogen environments are associated with each of these compounds, and we'll be referring to these compounds continually during lecture tomorrow evening.